Okay, I was given a tough task of going after Skylar, but I'll do my best. Hi, so my name is Mina. I lead the algorithmic design group in CSAIL at MIT, and our group is all about designing things with algorithms. That's why we name it that way. And design for us means pretty much anything. We design materials, we design structures, we design architectural things, fashion things, but we also design drugs, antibiotics, new neural network architectures, and all sorts of things. So today I will talk about inverse design because that's the most common thread in our group. And here we design so many different things. So the flavor of today's talk is going to be covering different kinds of projects you can do with computational aspects, with designing things with algorithms. Okay, so I will be talking about how we use geometry processing to enable us to design things with auxetic structures, something related to what Skylar was just talking about. Then I will talk about how we use deep learning to design terrain-optimized robots. And finally, I will briefly cover how we can also apply data-efficient machine learning for automated optimal experimental design, which can be used for drug design, for vaccine design, for designing new business strategies, and all sorts of things. Okay, so let's dive into the first topic. So first of all, what are auxetic materials? They're these engineered materials that have this weird behavior. When you stretch them in one direction, they also expand in the other direction. So they have this negative Poisson ratio. And they've been studied by Nike for shoe soles, by BMW for concept cars, for electronically actuated devices, for art, fashion, and so on. But the problem with all these examples we've seen so far is that they're limited to very simple geometries. So our question was, can we approximate any kind of complex surface taking a sheet of auxetic material? Now, what is the challenge here? So let's say we have a complex surface of a face of Max Planck, and we want to stretch the sheet around his face to get the approximation of it. So if you look at how this material behaves, in this example, we just take a thin sheet of plastic, and then we introduce a regular pattern of slits in it, and now it can stretch. It gets this negative Poisson ratio, so it expands in all directions uniformly, and we can wrap it around doubly curved surfaces, for example, a sphere. We can approximate complex geometries, but if we just naively take a sheet of this material and try to wrap it around the head of Max Planck, in most cases we will fail badly. And that's because of the global coupling happening in this material. So if you stretch the material on one side, you have no idea how it will react on the other side because everything reacts like a linkage, so everything is connected with each other. So we went back to studying the material in more detail, looking at its properties, and what we noticed is that the material scales isotropically, which led us to think of conformal geometry, something that in computer graphics, which is my base area of study, we use it a lot for texture mapping and other things, but it actually matches nicely to this kind of isotropic scaling to uniformly mapping materials. Now, what conformal geometry gives us, in the interest of time, I'm not going to go into too much details, but basically what it allows us to study is, given a 3D surface, when looking at it locally, how it curves, what are the features that it has, we can compute how much scaling we need locally in the 2D material to approximate a given surface. Now, if we want to fabricate a mask for Max Planck, because we are geeks, we take the 3D surface as an input to our algorithm. Then the algorithm automatically computes, taking the conformal geometry and optimization system inside it, automatically computes what is the 2D layout of this auxetic material that you need to approximate the surface. Now note that it has this very unintuitive cut in the middle that now it goes on the tip of the nose to approximate the surface. So there is no way you would manually think of the structure on the bottom left to be the 2D sheet of material that you need to approximate a face of Max Planck. So everything was enabled just by an algorithm, an optimization algorithm that does everything automatically. Now we can also make, for example, a high heel shoe made of aluminum sheet, aluminum auxetic sheet. We can also use it for fashion, and here we make a top with a leather piece that it has this cut to become auxetic. We can also use it for shading systems, where now you can also control the amount of opening locally that you need in the structure. You can approximate these free-form surfaces and get interesting looking structures. And also a very nice feature of this material is that it's also transformable. So if you take a single sheet of this auxetic material, you can approximate many different geometries with it. Now, as much as this is interesting for several applications, it is also a little bit challenging to make the material go into exactly the prescribed shape that you get out of the algorithm. So you need to make sure that all the openings are exactly matching what you computed with the algorithm. And that led us to our next research question, which was, can we actually encode a unique 3D shape inside of the 2D material without any need for scaffolding, any need for guiding the surface to go to the right direction? Can we program it into the 2D sheet of material and then just actuate it with some mechanism to get the final shape? And that is what we did with programmable auxetics. So the idea is that we encode the maximal local stretching in the material by controlling the sizes of these linkage triangles, and then we encode the features of the surface by using the conformal geometry to locally know how much we need to stretch to approximate a given target shape. And another thing that we need to incorporate, as Skylar discussed as well, is we have a piece of material, but we need to actuate it with something. And in this case, we use inflation as the actuation mechanism because we have the local stretching, the maximal stretching that we can get, but then we need to stretch everything out to its maximum to get the final 3D shape. So here we take the target shape, we apply the optimization algorithm to get what is the deploy state of the material, and then we get also what is the optimized flat state. Now, when we fabricate this with just simply laser cutting, we then have to inflate it to its maximum, and it will go to the prescribed shape. Now, this is interesting because you can create, for example, a Mars habitat, because habitats on Mars anyways have to be pressurized because the difference in the pressure on Earth and at Mars. And you can conveniently pack this 2D sheet of material in a box, ship it to Mars, and then without any scaffolding, you just have to inflate it to its maximum, and it will go to the prescribed shape. And because we can control, we can approximate any kind of 3D surface, you can easily have a control over what is the kind of shape you want to make. So let's say I want to have one room that is going to be big enough to store all the equipment that I need, like robotic structures and so on, and a smaller room where I can sleep and keep the temperature, right, and so on. Okay, and then another interesting application we found is in medical devices. So heart stents are typically made regular and straight cylinders, but the study from 2016 discusses how this can be problematic for patients which clogged vessels are curved. And now with our approach, we can conveniently scan the heart of the patient, detect the problematic vessel, and then automatically reconstruct the 3D shape of that vessel that needs to be unclogged. And then again, automatically with the algorithm, reconstruct what is the 2D material that is patient-specific and that can be inserted. And once inflated, it will go to the curved heart stent. Okay, so this concludes my story on the auxetic structures. Now, because we're at MIT, it would be a little bit weird not to talk about any AI, so I had to include the other two topics today. The second one is on using deep learning to design robots. So most of us have seen different robots in the news, on Instagram, or if you're lucky and you can work with some of them, you've seen them in person. And they're typically made by engineers who are pretty experienced, but still have to go through the trial and error to make the structure, then test it, see if it performs the way they wanted it, then go back, adjust the structure, and so on until they're happy with what they get. And the structure of the robot determines its capabilities. So different kinds of structures are designed to be able to run different terrains here. But our question was, can we have an automated design where we can discover what is the most optimal robotic structure to run on a given terrain? So the input to our algorithm is a set of components you can use to build a robot. So you maybe have some off-the-shelf things, you know what kind of links you want to use, what kind of joints, what are their limitations, masses, and so on. And then another input is what is the kind of terrain you want your robot to be able to traverse. So let's say I have an unevenly stepped terrain, or I have some wall obstacles, some ridges, maybe a frozen terrain, and so on. So the question is, how can we actually determine what is the right structure of the robot, what is the design that will be able to run on this terrain as fast as possible, but also be built from the given components. And the way we describe the whole design space of possible robots is by using graph grammars. Now let me first say why graph in this part. So we can nicely represent a robot with just a simple graph, where each node of the graph represents a different part of the robot, and edges are just the connectivity between these parts. Now, once we have this representation for the robot, then we can use graph grammars to describe the derivation rules of how we can build different kinds of robots. So I'm not going to go into too much detail here, and the slide is cluttered. It's not, my goal is not for you to understand every single detail, but the point of this slide is to say, with this simple set of rules, we can design hundreds of thousands of different robots. So with just these 7 structural rules, we control how to build robots that are all able to walk. There is no collision. We can fabricate them, build them in reality. And this, by using this grammar, by choosing different set of rules or different order of the rule applications, we will get different structures, and we will get hundreds of thousands of them automatically. Now, here are just some examples of the variety of robots we can get with this grammar. But now the problem with all these structures is that they're not optimized robot structures. So they're not optimized for a given terrain. Now, what do I mean by that? Well, let's see, for example, this little fella with extra long limbs. It's not the most optimal for crossing bridges. It can still do it, but it's not the most optimal. The other one, for example, with wheels, it has this added mechanism to be able to climb, but it would be much faster going downhill than climbing stairs. Now, this brings us to the final step of our algorithm, where once we are able to generate this huge space of robotic designs, how do we actually identify what is the most optimal one for a given terrain? And that brings us to AI, or using neural networks to actually be able to speed this up. Because if we were to simulate hundreds of thousands of robots and just apply a greedy approach to test every one of them and check which one works the best, it would take us years to run this kind of thing. So the way we do it, we have a selection of training samples shown on the left. So we use several thousands of them. We know how they perform because we simulate them. And then we feed them into a graph neural network that then learns to predict how is the performance going to look like for unseen robots, and also for for robots that are partially complete. So the ones that are not even completely finished so that they can run on terrain, but rather taking just the body parts and then adding some legs and so on. Now, by using this graph heuristic search that we developed that works on graph neural networks, we are able to find structures like this one, for example, that is optimized for avoiding a set of wall obstacles. Now, an important thing to note here is that as a human, you would never manually design a structure like this. It's completely unintuitive, but it actually proves to be way more efficient than any conventional design that we see around. Or this one, for example, is optimized for an unevenly stepped terrain, which is one of the most challenging ones for robots to traverse. It has these front hooks for climbing and simple back legs to save the energy. Okay, and now let's quickly move on to the last talk, which is on data efficient ML, which we use for automated optimal experiment design. And the whole research here was inspired by the project where we were trying to design new 3D printing materials. So what we had in our setup is a set of chemical ingredients that we have to mix together in a certain ratio. And depending on their chemical reaction and on the mixing process and on the printing process, they will have a different performance once fabricated. So we have to mix these chemical ingredients. We have to 3D print them. Then we have their mechanical performance tested on an instrument machine. And only after that, we can find out how different mixture of these materials works, or what is its performance. So there is no way to intuitively know upfront how a small change in some chemical ingredients will have an effect on the mechanical performance. Now, the way this is done in industry is you have engineers with many years of experience going through the trial and error approach, trying to fix what are the compounds you use and so on to improve the behavior. But what we were looking at, because we are grad students and postdocs that have a limitation on the amount of time we need to use to publish something, we were looking at a more systematic approach to discovering better performing materials. And the way we do it is by using an optimization algorithm that actually guides this search. So our budget on the number of samples was pretty limited because we can only print and cure and test one sample per day. We could use only around 150 samples to train our model that will predict how an unseen sample will behave. So it is a really data efficient ML approach. And the optimization strategy we use here is called Bayesian optimization, and we actually were able to develop several of our own algorithms in Bayesian optimization space. But the idea is that Bayesian optimization proposes what is the next sample to be tested. And it proposes it in a way that you most efficiently improve your predictions of how the unseen designs will react. Now, you can immediately see that this has potential applications in many different fields. One of them that we are really interested in is material science, but also, for example, in robotics, it's pretty powerful in tuning the hyperparameters for neural network, in engineering design, trading strategies, and so on. And because we noticed this is such an interesting field to work in, we also developed a UI, a user-friendly GUI, where you don't have to have any experience with optimization or machine learning whatsoever, but it's a pretty intuitive way of just setting up what is the number of your design parameters. You can choose what kinds of parameters you have. Is it continuous parameters, binary or categorical? Then you can select what is the number of objectives you have. Are you trying to minimize them or maximize them? You can add constraints and so on. And then the tool will guide your search for the most optimal design. So here I'm just going to fast forward a little bit through, if I can. No? No, I'm sorry, I cannot fast forward through the video, but anyways, I highly encourage you to look it up on our webpage. It will be in the final state by the end of February, so a little bit patience and you'll be able to play with it. And we're of course happy to chat anytime if you have any insights on how this can be improved. Okay, so this concludes my talk. Before I end, I would also like to mention that I'm leading a group of very fun students, so please come and hang out with us. We're happy to chat about any kind of collaboration or any interesting topics. And we are a young group, so pretty much all of them except one started 5 months ago, and it's yet to be seen what will come out of our group. Okay.